Hello class, and welcome to the lecture on section 4.5, the normal distribution. Now, the normal distribution is probably the most important distribution we're going to study in this course. Reasons why? Well, because the normal distribution is, I'm going to say, the most popular distribution in statistics. It is the one that we ideally want to have our populations from, and it has some really nice properties that make working with it very nice, some of which we'll talk about later in this course. So this is a section you're really going to want to pay attention to, and you might want to read this section more than once in your textbook. So getting started, normal distribution for importance in statistics. One thing right off the bat, some variances are normally distributed. This is something that pops up a lot in Stat 312 if you end up taking that. Two, the normal distributions have some nice properties that are useful in statistical inferences, and I've kind of already hinted at that already. So what the normal distribution looks like is we can see it in this graphic right here. We have a nice symmetrical mound or bell-shaped curve. In the center of this curve, we have our mean mu, and you can notice we have these line segments that are to the left and right of our mean, our population mean specifically. And if you look closely, you can see that it's there. If you look at the writing, it says mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and on the left-hand side, you see the same thing, only it's minus sigma, minus 2 sigma, and minus 3 sigma. So this is an important thing for you guys to understand, that standard deviation, when we're talking about the normal distribution, you can almost think about it as a unit of measure, the same way you think of inches and feet. And what's really nice about this normal distribution is that when we're looking at the normal distribution, there are an infinite number of normal distributions depending on whatever their mean and their standard deviation is. But what we can do is we can convert it into something called the z-score, which we'll cover in this lecture. And what that z-score does is it converts anything, regardless of its original measurement, into standard deviations, and specifically into the normal distribution where the mean is 0 and variance or standard deviation is equivalent to 1. So it has these, like I said, it has this really nice property. So if we want to compare something to, say, feet and time, one nice example is with a track. Someone's trying out for track and they want to see if they are a better runner or are they better at throwing the javelin. And so you can measure how far they can throw the javelin and how fast they can run. So we're doing, I apologize, I never did track, so we're just going to assume it was inches that they measure. So inches versus time, and you can't really compare those two, but what you can do is you can figure out, okay, how well did I do throwing versus how well did I do running, and convert those into standard deviations, which gives them the same units, which you can compare against. But like I said, I'm getting a little ahead of myself, and if I lost you a little bit there, that's okay. We'll come back to it with some nice examples. So let's talk about first some properties of the normal distribution, and I've kind of already hit on some of these. So first off, our distribution is mound or bell-shaped. 2, it is symmetric about mu, the population mean. Your data must be continuous. 4, the total area beneath the normal curve is 1. 5, there is infinite number of normal distributions, each with its own mean and standard deviation. And finally, the notation we like to use for this is x, or whatever our variable name is, tilde capital N, and then in parentheses, we have our parameters for mean and variance. So to give you an example, or two little examples of what this can look like, is so we'll let, for our example one, let x be part of the normal distribution, and we are given that mean is 50, variance is 25, which implies our standard deviation is just going to be 5. So if we look at our normal curve, our mean is the center, which we are given that mu is 50, so at the center of our normal distribution is 50. And with each of our line segments, those represent one standard deviation more away from our mean. If we are looking at the right, we like to say that that is however many standard deviations above the mean. And if we are looking to the left, that means we are talking about how many standard deviations are below the mean. So one tick mark to the right, we have mu plus sigma, so that is one standard deviation above the mean. And how we can figure out that value is our standard deviation is 5, mu plus 5 is 50, plus our standard deviation of 5, which equals 55. We can do the same thing for mu plus 2 sigma, that would be 50 plus 2 times 5, which equals 60, and same for 3 standard deviations. 50 plus 3 times 5, which would equal 65. And notice we can do the exact same thing going below our mean. First one says mu minus sigma, so that would be 50 minus 5, which equals 45. Again, 50 minus 2 times 5, which would equal 40, and one last time, and we will get 35. So each of these tick marks show one standard deviation more above or below the mean, depending on its placement. Let's take a look at a second example to really hit this idea home. So we have x being a part of the normal distribution. We have mean equal to 75, variance equal to 64, which would imply that our standard deviation is 8. So we start again at our center with our mean of 75, and what we can do for each direction to the left or right, subsequently add 8 or subtract 8 to the previous value. So 75 plus 8 would be 83, plus 8 again would be 91, plus 8 again would be 99. And then going in the opposite direction, starting at 75, we can subtract 8 and get 67, subtract 8 again and get 59, and subtract one more time and get 51 for 3 standard deviations away from the mean. So 51 is 3 standard deviations below the mean. Very nice. Okay, so let's take a look at something called the empirical rule, which kind of gives you an idea why we mark things the way we mark them. So the empirical rule is also sometimes known as the 68, 95, 99.7 rule. And what it says is that 68% of your data is within one standard deviation away from the mean, and that 95% of your data is within 2 standard deviations away from the mean, and that lastly 99.7% of your data should be within 3 standard deviations away from the mean. This will come in handy sometimes when we are trying to calculate probabilities. If those probabilities can fall within the 68, 95, 99.7 rule, we can use our rule to calculate the probabilities. And I realize that statement was very circular, but you'll see what I mean when we do a couple examples. So let's start off with this one. So suppose X, the weight of a full-grown dog, is normally distributed with mean equal to 44 pounds and standard deviation equal to 8 pounds. We want to find the probability that a randomly selected dog weighs less than 50 pounds. So probability of X less than 50 is going to equal the area beneath the curve to the left of 50, which we can see in this graph above. Now, using our 44 pounds for our average and 8 pounds for our standard deviation, we can make our tally marks as we did in the previous two examples. Now, unfortunately, 50 does not fall exactly on one of our standard deviation line segments of 52, 60, 68, 36, 28, or 20. If it did, finding the probability would be very, very quick, but unfortunately it's not. So let's talk about a second way we could do it. So it is impossible to construct tables for every normal distribution. Instead, we construct a table for a very special normal distribution called the standard normal distribution, where mu equals 0 and sigma equals 1, and then translate the original probability question to an equivalent question involving the standard normal distribution. So what we have here is something known as z-score. And z-score equals our value of x minus mu, our population mean, divided by sigma, our standard deviation. And this is our method of converting between our different normal distributions. So we let our notation be z tilde n 0, 1, and again, we refer to this as the standard normal distribution. We usually let z represent a variable which has the standard normal distribution, and note table 3 gives us cumulative standard normal probabilities. I'm not sure about you guys, but in my textbook, they actually have it labeled as table, oh, where's the page? So in my textbook, it starts on page 811, and it's actually labeled as, oh dear, did I just, there we go. I don't think you guys probably, I think I accidentally minimized my screen, but I think for you guys it actually just stays when I'm recording. I think it stays on the same screen, so that would have been nothing to you. But anyways, for me in my textbook, it's on page 811, and it's actually labeled as table A2, and it might just change based on the edition of the textbook you have. But if you're ever interested in just Googling it, you can either Google normal distribution table or Z table, and it will usually pop up what you need. So applying this to our dog example, if you think back, we have a mean of 44 pounds and a standard deviation of 8 pounds. We're asked to find the probability of X less than 50. So 50, that is what we are going to put in for our X value into our z-score formula. So plugging in X equals 50, mu equals 44, and sigma equals 8, we'll get a z-score of 0.75. So we say that the probability of X less than 50 equals the probability of Z being less than 0.75. Now this is the part where we need to use our standard normal distribution table. So if you're looking at that table, and I'll have a little Z here, you're going to have numbers along your x-axis and numbers along the y-axis. So to find 0.75. For me, this is going to be, this particular one is on page 112, and along our y-axis, you will find 0.7, and then, so along the y-axis, 0.7, and then on your x-axis, you'll have 0.05, and that spot where those two values meet, you will have 0.7734, and that is the probability of z being less than 0.75, because this cumulative normal distribution always measures to the left of whatever z-score we find based on the table. So in this case, this one. And that's it. That is how we can find the probability of x less than 50. Again, steps. Look at our probability. Plug into our z-score formula. Rewrite our new probability. Find it on our z-table. Get our solution. Let's take a look at another example. In this case, we'd like to find the probability that x is greater than 60. So, same steps, plugging in 60 into our z-score formula. We're going to assume this is a continuation of our dog example. So that means we have mu equal to 44 and sigma equal to 8. So plugging in 60 minus 44 divided by 8 for our z-score formula will give us z equals to 2. Plugging that back in, that means we're really going to find the probability that z is greater than or equal to 2. Now, unfortunately, as I explained in the previous example, our normal cumulative distribution table gives us the area to the left of the curve. This, asking for greater than, is asking us for the area to the right of the curve. Well, kind of a problem, but not a big one, because if we look back to our properties, we know that the total area beneath the normal curve is 1. So using that same rule of our complement that we did with probability, in order to find the probability of z greater than 2, we really just need to find the probability of 1 minus the probability of z less than or equal to 2. That we can find easily. So 1 minus, and in order to get this 0.9772, that's going to come from our z table. So remember, looking at our y-axis, you're going to go, it'll be pretty far down. You're going to get 2.0. And then along the y, we will also be looking at 0. If we do, we will get 0.9772. And so 1 minus 0.9772 equals 0.0228. So the probability of x greater than 60 equals 0.0228. Excellent. Now, I will say we could have gone about this one slightly different, because we had a z-score of exactly 2. So if we scroll up, this is where our empirical rule of 68, 95, 99.7 rule comes in. So we had a z-score equal to 2. That puts us right here. See, 1, 2 standard deviations above the mean. What we could have done is using our empirical rule, we could have just added up our probabilities of, so 0.15 plus 2.35 plus 13.5 plus 34%, 34%, 13.5% to get our probability of z less than or equal to 2. But our original problem actually asked us to find greater than 2, which is even easier to calculate because we could have just added up this half. So the probability of x greater than 2 would have just been 2.35% plus 0.15%. Add it up, so 2.35 plus 0.15 would give us 2.5%, which if we made that into a decimal, would be 0.025, which if we compare to our calculated, not too far off. So using our empirical rule, we were off by only a couple hundredths. And that's normal because the empirical rule is a rounded estimation, but it is an alternative way for you to go about solving this problem, and either method is acceptable. Okay, so since we've done that, let's take a look at another example using our same dog example. So let's say we want to find the probability that 50 is less than x is less than 60. Well, we've already done the z-score for both of these, but I'm going to do it real quickly anyways. Just to remind us where our z values are coming from. Okay, so for 50, we have a z-score of 0.75, and for 60, we can get a z-score of 2.00. So equivalently, that means we can find the probability of 75/100 less than z less than 2. Now, in order to do that, same rules that we did when we were doing our cumulative distributions and our probability density functions, so our CDFs and our PDFs, we can subtract. So the probability of z less than 2 minus the probability of z less than 0.75. We found both of these probabilities already in the previous problems of 0.9772 minus 0.7734, which would give us 0.2038. So again, to find the probability of 50 less than x less than 60, convert to our z-score, find the probabilities in our table, and then subtract. Oh, this is the same side twice, so we can ignore that. Okay, so last one of these, using this dog example, is asked to find the probability that x is less than 40. Now this is going to be a little bit different because 40 is actually below our mean. So the process is still going to be the same. We have z equals x minus mu divided by sigma as our z-score formula. Plug in, so we'll have 40 minus 44 divided by 8. And this will give us a z-score of negative 0.5. So still plugging in, that means our new probability is going to be the probability of z less than or equal to negative 0.5. And that negative 0.5 is saying that we are going to be 0.5 standard deviations below the mean. And we can still find that in our z-table on page 811. Looking at the y-axis, more towards the bottom, we have negative 0.5. And then up at the top, it'll be 0.00. And we will find at our point of intersection of 0.3085. So the probability that x is less than 40 is going to be 0.3085 or 30.85%. Okay, not so bad. So that's one way or one direction we can say of using our z-table. We can also use the z-table in reverse. So instead of finding the probability of x less than b or the probability of x greater than or equal to a, we are given a probability p and find an x value from a normal mu sigma squared distribution. So steps to doing this. Step 1, find z such the probability of z less than cursive z less than z equals p. Step 2, plug in z, mu, and sigma into our z-score formula, and then using algebra we can solve for x. So as an example of this, suppose x belongs to the normal distribution with mean 50 and variance 100. So right off, that's going to imply that our standard deviation is equal to 10. And we want to find x such that the probability of x less than x equals 0.975. So we'll use our table to find z such that, again, the probability of z less than z equals 0.9750. Okay, so step 2, we are going to plug into our z-score formula. Oh, nope, sorry, got ahead of myself. Okay, so we know that we're trying to find the probability of z less than z equals 0.9750. So using our table, we actually are going to have to go and find the 0.9750 in the table, or at least as close as we can get to it. So somewhere in our z-table, we have 0.9750, or again, as close to it as we can get. And for me, that one's going to be on page 812, or it's going to be on the second page. And so looking. All right, so, and what happens is just how before we used our x and our y axis and found that point of intersection, and that was our probability. We are going to do that the reverse. We're going to use the probability that we know to find our z-score value. So I have found in the z-table the 0.9750. And if I look at the y-axis, going straight across, I have 1.9. And if I go straight up the column of the 0.9750, I have 0.06. So that implies that my z-score is going to be 1.96. So good, I have that value to plug in. And from the problem above, I know that my mean is 50 and my standard deviation is 10. So I'm ready to plug in for step 2. So step 2, plugging in for z-score, we have z equal to x minus mu divided by sigma. Solving for x, we have 1.96 equals x minus 50 divided by 10, which we would solve for x to be 69.6. So therefore, for x to be a part of the normal distribution with mean 50, variance 100, the probability of x less than or equal to 69.6 equals the 0.9750, or as I keep wanting to say, 97.5%. Very good. Not bad. Let's do it another time. So let's find an example. Let's find x such that x is greater than x equals 0.1587. And this time we will rewrite our problem because, again, our z-table only gives us the area to the left of the curve, not right. So greater than can present a bit of a problem. So we have the probability of x greater than x, which we know would be equivalent to 1 minus the probability of x less than x. Plugging in for our given probability value, that would be 0.1587 equal to 1 minus the probability of x minus x. Simplifying to make our lives easier, that'll give us really what we're trying to find, which is the probability of x less than x equals 0.8413. So now we need to find our z-score using our z-table. So if I take a look, I want to find the closest value to 0.8413 in my z-table. Oh, there we go. That one was pretty easy. And that's going to give us a z-score of 1. And just to remind you, so in our z-table, we had 8413. If I go straight to my y-axis, it is 1.0. And if I go straight up that column, I have 0, 0, 0. So that tells me my z-score is going to be 1.00. Now, step 2, we're going to substitute in our known values of z equal to 1, mu equal to 50, and sigma equal to 10. Solving for x, we will get x equals 60. So that means that the probability of x less than 60 equals 0.8413. Very good. All right, moving right along. Let's talk about a theorem because let's take this a step further. So suppose x1 all the way to xn is a random sample from a normal distribution with mean mu and variance sigma squared. The sample mean, x bar, is an unbiased estimator of mu, and the sample variance, s squared, is an unbiased estimator of sigma squared. The mean of the distribution of x's possible values, the sampling distribution of the sample mean, is mu x bar equal to mu, and the variance of the distribution of x's possible values is sigma x bar squared equal to sigma squared divided by n. And also our sigma x bar equals to sigma over the square root of n. It's sometimes called the uncertainty in x bar. Another theorem. Suppose x, that's part of the normal distribution of with mean, mu, and variance sigma squared, and a and b are constants with a not equal to 0. Then y equal to ax plus b is a part of the normal distribution with mean au plus b, or not u, excuse me, that should be u, not u. So with the normal distribution with mean a times mu plus b, comma, variance a squared times sigma squared. To put this into an example, water temperature at Lake Stat on the 4th of July was recorded for 80 years and follows a normal distribution with mean 81 and variance 16. And just so I don't forget, that means our standard deviation would be equal to 4. And so we have a normal distribution with mean 81, variance 16 on a Fahrenheit scale. And the formula to convert to centigrade is C equals 5/9 times the quantity of F minus 32. So if we were to simplify this equation by using our distributive property for the 5/9, we would get that C is equal to 5/9 F plus negative 160 over 9, which should hopefully look familiar to the theorem we just did with our ax plus b. So for this problem, that means a equals 5/9 and b equals negative 60 over 9. So that means that mu of c equals a times mu for our Fahrenheit plus b. So plugging in based on our rules to get our normal distribution, we know that we can plug in for our mean of our centigrade to be 5/9 times the mean for the Fahrenheit plus negative 160 over 9. The mu for the Fahrenheit is 81. Simplify. That means our mu for our centigrade is 27.222. Continues. Similarly, for variance, we know that the variance for our centigrade should be a squared times the variance for the Fahrenheit. Plugging in from our known values, we'll have our variance for the centigrade to be 4.938. And if you're curious, we can also do the same thing for our standard deviation. Because if you recall, thinking back to a couple sections ago, this would have been the absolute value of a times variance for our Fahrenheit, which would give us a standard deviation for the centigrade to be 2.22, repeating, or not repeating, but continues. So putting in what we already know, that means C for our centigrade should follow the normal distribution with mean of 27.2 repeating and variance of 2.2 repeating squared. Couple little notes. Note, a linear transformation of a normal random variable will yield a normal random variable. Also, we can extend this concept to linear combinations of independent normal random variables. To show this, let's take a look at another theorem. So suppose x1, x2, all the way to xn are independent and normally distributed with means mu1, mu2, all the way to mun, and variance sigma 1 squared, sigma 2 squared, all the way to sigma n squared. And let C1, C2, all the way to Cn be constants so that y equals C1x1 plus C2x2 plus ... plus Cnxn is a linear combination of x1 all the way to xn. So that means then y is approximately normally distributed with the mean for y and the variance for y, where the mean for y equals C1 plus mu1 plus C2 times mu2 plus ... plus Cn times mun. And the variance for y is C1 squared times sigma 1 squared plus C2 squared times sigma 2 squared plus ... plus Cn squared times sigma n squared. So to put this into an example for us, let x1 be normally distributed with mean 5 and variance 2 squared, and x2 be normally distributed with mean 10, variance 3 squared, and x3 be normally distributed with mean 15 and variance 4 squared. And they are independent. We have C1 equal to 1, C2 equal to negative 1, and C3 equal to 2. So that means or implies that y equals 1 times x1 minus x2 plus 2x3. And therefore, it has mean mu of y equal to 1 times 5 minus 1 times 10 plus 2 times 15, which would equal 25. And therefore, using our variance rule, or expanded variance rule, our variance of y would equal 1 squared times 2 squared plus -1 squared times 3 squared plus 2 squared times 4 squared, which would equal 77. So therefore, y would have a normal distribution with mean equal to 25 and variance equal to 77. Not bad, really just an extension of those rules we looked at that previous example. Okay, so to wrap this up, let's finish with a lovely little lemma. Suppose x and y are independent, with x being normally distributed with mean x and the variance of x, and y is normally distributed with mean and variance for y. Then x plus y is approximately normally distributed with the mean of x plus the mean of y and variance of x plus the variance of y. And similarly, x minus y would be normally distributed with the mean of x minus the mean of y and the variance of x plus the variance of y. If you notice, you might be questioning this being addition. Whenever we are comparing variances, we always add. That is not a typo. That should be an add. I know it seems a little weird, but yes, whenever we compare variances, we always add. So last thing we're going to talk about is a theorem to wrap us up. So suppose x1 all the way to xn are independent and normally distributed with mean 0 and variance sigma squared. That means that x bar, our sample mean, is approximately distributed with the mean of our population and variance of our population variance divided by our sample size. And so we don't forget. So again, U, that is our population mean. X bar, that is our sample mean. And sigma squared, that's our population variance divided by our sample size, which I feel like brings a lot of things full circle, and you are definitely going to want to make sure you know that lemma and that theorem going further. Okay, so that takes us to the end of the normal distribution. We are not truly finished talking about it because you'll hear me mention it numerous times throughout the rest of the semester, but that's it for this one. Have a good night, everybody.